Welcome! In this series of videos we will cover the design and implementation of a project, from initial design through coding and development to testing, using either the PowerBasic Windows or console compilers. Today we will look at doing some code optimization of our star migration simulation. This was our application at the end of the last video. This is star migration. This creates a globular cluster of stars and rotates them round a central black hole. When creating simulations and applications in general, after you've created the first cut of the application, you may want to optimize it to make sure it's running as efficiently as possible. However, in order to do an optimization, you first need a baseline, a metric against which you can measure any improvement in performance. And that's what we're going to do first of all. If we go to the pb-main function, this is where our application begins. So we're going to create a local variable to allow us to record the start time. And we'll make this variable a double. And further down the code, where we initialize the stars, we're going to populate this variable using the timer command word. And after we go through each cycle, we want to update on screen what our average frames per second actually is. So we're going to do our graphic colour to change our foreground colour to cyan. We're going to set the position on screen at 1050 and we're going to print out our average frames per second. This is going to be the year count, which is the counter for our for next loop, divided by the timer minus the start time. If we run the application now, we can see we're getting about 36 to 39 frames per second. So this is our metric. Now we can actually look to see where in the application we can make improvements. So let's get back to the code. As you will remember, at the beginning of our code we have a number of constants. One of these constants is the star count. This is the number of stars to seed our simulation. Currently this is sitting at 100 stars. If we can radically improve the performance of our application to get the frame count up, we can increase the number of stars we're processing. So in order to achieve an improved performance, we'll need to do some pre-calculation of some values used within the application. We're going to put some more constants in place. These constants will first of all be the minimum distance squared. This is a minimum distance squared to prevent any divisions by zero. The next is max inference distance. I'm setting this to an arbitrary 1000. This will probably make no difference to the application at the moment, but it can be useful later on. And the final constant is colonization check interval. This we will use to set when we check for colonization. We won't be using this in this video, but it will be for a future one. The main star data is basically unchanged. This is the user-defined type that's used to keep track of each star. We are, however, going to create a new UDT to allow us to pre-compute values for optimization. This will have three values: the gravity mass, the screen X coordinate and the screen Y coordinate. These are all going to be pre-computed to allow us to speed up the application. And as we have a global array for the stars, we're going to have a global array for these pre-computed values. And there it is there, defined as UDT pre-computed. Next, we want to have some global variables to allow for our optimization. And here are our three optimization variables: one for gravity, one for viewing distance, and one for the maximum inference distance squared. So as we now have a new user-defined type, we're going to have to dimension it. And we'll do this within the pb-main function. And there we have populated our three new global variables. And we're now dimensioning the pre-computed array by the number of stars. So this will sit alongside the main stars array. So within our for next loop in the pb-main function, we're going to make amendment to the move stars function. To make this easier, I'm going to create a brand new function called move stars optimized. This, as before, takes a single variable, which is the year count. So let's now create this new function to move our stars. It will be very similar to the function we had before, but we're going to change things around a little. As we have pointers to the star data array, we'll need some pointers for the pre-computed array also. And we're going to need a few more local variables. Now we get to populate the pre-computed array. This allows us to work out the gravity mass by multiplying gravity by the star's mass. So this only needs to be calculated once. It doesn't have to be calculated within each iteration of the processing. And within our nested loop, where we're setting up the pointer to the stars array, we'll also need to set up the pointer to the pre-computed array. Like so. Now we can go ahead and start calculating our distances. And in this section where we're simulating the colonization, we'll make a change in here so it's no longer hard-coded. And at the bottom of this function is a call to the place stars function. We're going to optimize that as well. But before we do that, we're going to call a new function called pre-compute screen positions. This new function will pre-compute screen positions for all of the stars. This is a more efficient way of doing the processing. We will work out where the stars are going to go and then place them based on that information. So we will optimize the place stars function in a moment, but let's go ahead and create the new pre-compute screen position function first. This is going to be a fairly straightforward function, as it will use some of the logic that's currently in the place stars function. First, we need some local variables to keep track of our stars for the pointer, the pre-computed array as well, and also our depth factor. And we're going to be using a for next loop, stepping through each of our stars one at a time. So we're picking up the pointer to our arrays, and we're calculating the depth factor as the view distance divided by the view distance plus the z coordinate of our star, and populating our arrays with the screen position x and y coordinates. So with that in place, we now have to optimize the existing place stars function. So as before, we're going to be using a couple of pointers to point at each of our global arrays. One for the main star data array and one for the pre-computed array. In this function, I'm going to limit where stars can appear on the screen. This is to avoid them wandering into the right-hand side of the screen, where we're going to be showing metrics on how the empire's colonizations are progressing. So we're going to be doing a test on the x and y coordinates to make sure they're not greater than the x and y limits of our zone where the simulation is to take place. Next, I want to place both the black hole and all other stars on the screen. And we're using our pointers to do this quite straightforwardly. There's no great logic change between this function and its predecessor. We're just using pointers to make the code a little more readable. The next change I want to make is to the initialize stars routine. Within this function, there's a call to the empty star location function. This is to ensure we don't position two stars on exactly the same location. I want to add a little more to this to ensure that not only are they not in the same position, they're not too close. So we'll be optimizing the empty star location function and calling it empty star location optimized. So as well as passing x, y and z, we're going to add on the pointer to the star we're currently processing. So there is our new fourth parameter. So we will create this optimize function in a moment, but let's continue with the code we're working on. And now we can initialize the remaining properties of our array for the star. Its x, y and z coordinates, its mass, the color, the owner, which is currently 0, and the status, which is also 0. So the next function to tackle is the empty star location. Currently it has 3 parameters, so we need to amend that to add the fourth. So there is our new function with its 4 parameters, the last parameter being the current index, the star we're currently processing. And there is our minimum distance of 20 units. So if the star is too close to another star, it will look for another random generated location. So there's another function called place black hole. We'll make a few minor changes to that as well. And that is the function to place our black hole at the center of the simulation. Next we have the function to draw the map boundary. It currently sets the graphic width line to be 4 pixels, and then we draw the box on the screen. Just in case we're going to be doing any more line drawing, we'll reset the graphic width to 1 unit. So now that we've made all those code changes, will the code compile? And yes, it will. As you'll remember from the last run, we were getting about 38 or 39 frames per second. So let's try running it now and see what we get. And as you'll see, the average frames per second is now up to 64 frames a second. So we have doubled the output from our simulation. The stars are displaying quite nicely, and we're getting a faster update on screen. So now we can attempt to increase the number of stars and the length the simulation runs for. So we'll go back to the beginning of our application. We can change the star count, so let's move it to 200 stars. And we will increase the number of years by a factor of 10. So if we run the application now, we will see we are still getting 64 frames per second, but we have considerably more stars on the screen. And the application is now running long enough for the stars to start to become coloured. The empires are starting to expand. And the drawing on the screen is quite smooth. So we've now got a simulation that runs for 10 times the length of the previous one, and gives us a good illustration of where the stars are going to be going. As I said in the last video, the stars which are whitest are the ones which are heaviest. You will see we have 2 stars approaching the edge of the screen. And there it disappears when it gets to the yellow border. So the code we put in place to limit the display of stars beyond the yellow box is working correctly. And there's another one. While we're not displaying those stars on the screen when they go outside the yellow box, the position is still being updated in the arrays. So when the star does come back, it will appear back at the edge of the box and head back towards the black hole. So in summary, what we've achieved today is we have optimized the calculation of positions of all our stars. This allows us to display twice as many frames as we did in the previous version of this application. What we'll do in the next video is we will save each of these frames to disk as a file to allow us to assemble them into a little movie. However, that's it for today. Thank you for watching.